Hello and welcome to this presentation about the CE4CE pilot project in Leipzig. My name is Konrad Jentsch and I am Manager for Processes and Strategy at the Infrastructure Department of the Leipziger Verkehrsbetriebe GmbH, shortly LVB. This is the public transport company in Leipzig, Saxonia. Today I'll guide you through our pilot on predictive maintenance and digital infrastructure optimization in the frame of the Interreg project CE4CE. So let's start first of all with a short agenda. First of all, I want you to understand our pain points and motivation in Leipzig. In the second part, I want to explain what we are doing within this pilot exactly, and finally check with you if we are on the right track. Public transport infrastructure is under pressure. Aging systems, limited resources, and increasing demands require smarter solutions. We see digitalization as our opportunity to improve efficiency, sustainability, and long-term asset performance. Therefore, in Leipzig, our CE4CE pilot and action plan focus on developing advanced methods for monitoring and assessing infrastructure condition. We aim to detect faults and trends at an early stage, enabling timely and needs-based maintenance interventions. The development of suitable measurement and monitoring methods, together with the linking of damage patterns with sensor data, is the content of our pilot, which I will talk about in this presentation. The goal of our action plan within CE4CE is then to enable data-driven maintenance decisions tailored to the needs of our network. The key part of our action plan is the evaluation of the collected data to systematically assess infrastructure condition, derive trends and forecasts, and in the end, enable predictive maintenance. But let's come back to our pilot and what we are doing there. In our Leipzig pilot, we deliberately choose a monitoring approach based on relatively simple and robust sensors. Rather than relying on high-precision measurement at individual points, our concept focuses on identifying patterns within large volumes of operational data. This allows us to detect recurring fault signals and trends across the network, making predictive maintenance scalable and cost-effective. The model sensor setup was developed during several workshops between LVB experts and partners and leads to the equipment of 3 trams with rail-certified sensors. We installed edge computing units for local data processing and LTE gateways for real-time transmission, as well as CAN bus connectors for vehicle board computer data, all together provided by CI4Rail. And here, for the energy consumption assessment based on data coming from the CAN bus interface, our partner Kruch is responsible. We also installed vibration sensors at the pantograph for overhead line and pantograph interaction together with cameras facing overhead line track for first assessment in the event of anomalies and laser scanners on the roof for thickness and zigzag of the overhead line. For the assessment of this data, our service provider PantoHealth is responsible. Finally, we installed camera facing track and street surface together with the vibration sensors on the inner floor for condition of tracks analyzed by the service provider CMIT. These sensors feed data into platforms developed by the 3 service providers Kruch, CMIT, and PantoHealth, enabling automated analysis and visualization supported by our LVB experts. In our Leipzig pilot, the sensor system were installed in phases and tailored to the specific infrastructure condition of our network. Each component was selected to meet railway standards and is integrated into the vehicle documentation. This modular and certified setup ensures compatibility, scalability, and compliance with safety regulations. As already mentioned, follows our data collection a principle of broad continuous monitoring, using relatively simple and robust sensors. Instead of capturing isolated high-precision measurement, We focus on identifying recurring patterns within large volumes of operational data. But how is this analysis work? The analysis process of such a large volume of operational data, especially for acceleration data, consists of four main steps. The first step is the data preparation, where we collect, clean, and structure the sensor data. The second step is the cluster analysis. We group similar patterns to identify typical fault signatures. The third step is the model development. AI algorithms are trained to detect, anomalize, and predict infrastructure issues. And the fourth step is the validation, where the results are verified through physical inspections and expert feedback. For identifying typical fault signatures and patterns, the focus is on typical measured variables like acceleration level, uneven ride, and shocks. After developing and set up of the analysis models, we applied it to real operational data. Let's now take a look at the first results from our pilot for track condition. Along line 1, we identified several fault areas, including broken rails and poor track conditions. These findings were confirmed through visual inspections and served as a valuable input for further training and refinement of our anomaly detection algorithms. This iterative process improves both safety and efficiency. While the track monitoring already revealed critical fault areas, our sensor setup also enabled us to assess the condition of overhead line infrastructure. Let's now take a look at the first results from this part of the system. On the Delitzsch and Eutricher Straße along line 16, we detected shocks and arcing at section isolators. Adjustments were made to improve pantograph interaction and reduce wear. This shows the potential of sensor-based monitoring to prevent damage. One of the key outcomes of our pilot is the development of dashboard tools that support daily operations and decision-making. The dashboards provide a real-time overview of all measurement data, giving our teams immediate insight into the condition of the infrastructure. It enables the central linking of heterogeneous data sources, such as camera images, vibration signals, and system alerts, into one coherent interface. This allows for quick localization of anomalies and damages, helping us respond faster and more precisely to emerging issues. In addition, the dashboard visualizes the time history of fault patterns, which supports tracking, trend analysis, and prioritization of maintenance actions. Finally, it facilitates the creation of reports and work orders, making it a practical tool for both strategic planning and day-to-day maintenance workflows. In short, the dashboards are a major step toward integrating data-driven decision-making into our operational reality. So let's come to a first conclusion and have a look if we are on the right track. As the pilot is still in progress, I will give an interim conclusion for time being. We have achieved initial success in detecting of typical fault patterns. The early localization of damage points is possible and will be developed further. Validation through comparison with real inspection data is ongoing to improve the models. Data analysis from overhead line laser and energy consumption requires more time than expected. We see a reduction of subjective assessment through objective data. We are also convinced that we are already improved our documentation and traceability, and we see a potential for optimizing our maintenance planning. A reduction of unplanned maintenance measures is conceivable. And finally, we are sure that we are one step closer to achieving our goal of data-driven prioritization of measures. The findings mentioned in the interim conclusion lead me to the next steps within the pilot. At the moment, we are finalizing the analysis and model development for the overhead line, laser, and the energy consumption data. In parallel, we are expanding our damage classification and refining the predictive algorithms to improve accuracy. We will also evaluate the long-term performance of the system and assess its impact on maintenance planning. A key part of this phase is exploring how we can scale the solution to additional vehicles and lines across our network. To support decision-making, we will conduct a profitability analysis to understand the economic benefits of broader implementation. From the perspective of transferability, we can say that the modular architecture of our system makes it highly scalable. We can extend it to more vehicles and infrastructure segments with minimal adjustments. Integration into LVB's asset management and planning systems is already underway, ensuring seamless use in daily operation. Strategically, we are developing a parameter-based model to support scenario-driven investment planning. This will allow us to simulate different maintenance and renewal strategies based on real data. Finally, we are preparing for replication. The solution is designed to be transferable to other cities and transport operators. And we are already exploring new use cases such as monitoring passenger flow or environmental data to further enhance its value. Our vision is a sustainable shift towards data-supported decision-making. Digitalization is the key to resilient, efficient, and environmentally friendly urban mobility. CE4CE and this approach in our pilot project is helping us shape that future. Thank you very much for your attention. If you would like to learn more, visit our project website or feel free to contact me directly. Together we can make public transport smarter and more sustainable.